Go through is acceleration, because displacement, then we did velocity, and then we do acceleration. Right? That's the way we did it at the beginning of the year as well. So this is angular acceleration. It's given by the Greek symbol alpha. That is alpha, which is given by a fish.
All these symbols.
What's that?
I got some Greek
It
symbols.
said this is famous.
Okay, that's good.
They came up with physics it's a fish. The Greek.
No, not entirely. Most of the physicists were not Greek. I would say early on they were. The philosophers of science were mostly all Greek. But later on, a lot of Europeans.
So they
In terms of numerical values, hardly ever Greek. So, because remember, Greek was philosophy. It was how the world worked without numbers. Typically, that's how I did that. So. But they used Greek symbols because they didn't have anything they already used. So, this is alpha, and that equals omega f minus omega I over t. Same thing, because if we were finding the acceleration in linear acceleration, it'll be what? Final velocity minus initial velocity over time. All that this is angular velocity minus angular velocity over time. That's it. Okay? It's the same thing. So, omega must be in radians per second.
You said how it that part.
I would highlight the equation. You should also highlight the units, yes. Okay, everything's going to be radians per second when you do these calculations. Okay, that's where we want things to be. So, units of angular acceleration are in radians per second squared. So that's of alpha is radians per second squared. And then every portion of an object has the same angular speed and angular acceleration. Here's what this means. If you are driving down the road, okay, and you're taking a turn, let's suppose you turn right more. All those exits, if you've ever realized, thought about your tires and thought about how you can conserve the tread on your tires and how they wear different than the other side, since you don't want to take them off to redo them or pay the $6 to have them rotated. If you turn a lot right. You should go slower so you can conserve them. But when you turn right, okay, suppose you only turn with your left hand. Well, what's happening to the wheel up here in terms of the angular velocity and the wheel down here? Is it going at the same speed and velocity or in acceleration? So if I turn the wheel, is the entire wheel going at the same angular velocity?
No.
It would have to be. Because if the top of the wheel goes pretty fast and the bottom doesn't go fast because I'm not touching it, that circle is going to change from a circle into some odd shape because the wheel down here isn't turning. Okay? So the whole thing has to turn at the same angular velocity or the same angular acceleration or in the same angular acceleration. Okay? The whole object is going to turn the same time, the same amount, essentially. Okay? Those things help. You are tired. We're almost there, I promise. Okay? We're almost there, I promise. So, if you remember kinematics, that was really fun. Well, we get to do it again. Alright, there's that. Excitement. Here are the 4 equations that you can use. Okay? Nowadays, I don't have to explain to you how to use them because you guys already know how to use them, right? You pick the best equation to use based on what you have. So let me tell you the units real quick, that way you can figure out what you have. Okay, the first one, delta theta. What are your units for that? That's probably the hardest one. There's 3 options. There's revolutions, radians, and there is degrees.
Meters, rad.
Not meters. Meters is a linear term. This is angular. Okay? So,
Degrees.
for delta theta, your units are always radians. That's what we want when we calculate stuff. Yeah, you're exactly right. You can have degrees, you can have revolutions. But when you calculate stuff, you always want to have it in radians. That way you can get radians per second or radians per second squared. Okay? So you want it in radians. Omega I units for omega I? WI. Units for WI or omega I would be radians per second. Because that is a speed. So just like meters per second, this is a speed at an angle. Okay? Omega F, same units. Time, what are units for time? I know you guys will get this one.
Seconds.
Just seconds. Or 1 for 4. And then make it 2 for 5. That can be 40%. What is alpha's units? Maybe I think what is alpha? Rad per second squared. Radians per second squared. That is an acceleration, angular acceleration. Okay? So you know all the units. You know which is which. Now it's just going to take practice of looking at the different types of problems. Okay? You should know all the information. You've done these type of problems before. It's a matter of practice. Okay? This shouldn't be too overwhelming. Not a lot of new concepts. Let me say this and then yes. Okay? Because this is the last slide. This is go on practice. Ready?
Yes.
I'm ready too. There. There's 3 equations here. Okay, each of them relate, say, meters to radians, or meters per second to radians per second, or meters per second squared to radians per second squared. Okay, I did all 3 just now. So you're relating linear motion to angular motion, is what you're doing. Okay, that's these 3 slides. There's 3 different formulas for it, depending on what you're trying to find. If I want to know the linear acceleration, even if it's moving at an angle, maybe if it's moving in a circular path, you can find that with that equation. Okay? Let's go ahead and look at this problem. Go ahead. Let's look at this problem real quick. You will. So, a pottery wheel is accelerated uniformly from rest to a rate of 10 RPMs in 30 seconds. What is the angular acceleration in radians per second squared? So the first thing you always do is you write what you know. So in this case, where's the good ones? Dance okay. We know that accelerates uniformly from rest, so we're looking for our angular acceleration. Oh, that was bad voice. I got other ones. Uniform acceleration, we're looking for the angular acceleration. It says time, 30 seconds. Okay, it starts from rest. What is that?
0.
0. Exactly what they gave me. That's fun. 0 radians per second. That is the initial speed, angular speed. And then the final angular speed is WF, which is 10 RPM.
Angular acceleration.
Alpha is the angular acceleration. WF is the final angular speed. Okay, so whatever speed you end up, we're going angular here. So, one problem that we notice right away is 10 RPMs. We cannot have an RPMs. Anytime we do a calculation, it needs to be in radians, or radians per second, or radians per second squared. So, that is a speed, so this needs to be radians per second. So let's go and convert that. 10 revolutions per minute. We get rid of minutes. 1 minute on top, so that they cancel. That's equal to 60 seconds. And then we need to get rid of our revolutions and convert that into radians. For every 1 revolution, that is 2 pi radians.